Now we can move on and talk about the next simplest types of assets. Of course, the simplest type of asset beyond money is a loan that we talked about in the first couple of classes. So again, let's start with loans, or simple loans as they're called, and then gradually study their structure. And what we'll find through doing this is that it's going to be different to be able to compare loans that, let's say, end after 1 year, loans that end after 2 years, loans that end after 3 years. We're going to want to develop some metric, some way of trying to be able to compare how cheap or expensive loans are with different time frames. And we'll begin by describing a simple loan. So a simple loan, there's my ruler, has the following structure. Suppose it's a loan contract between you and me. So a simple loan is a contract that says something like, you give me some amount, let's call it P dollars now in the present corresponding to the letter P. That's the first part of the transaction. The second one is, I give you some other amount, F dollars in the future. So F is there for future, but let's just make it more concrete and let's say in 1 year. That's a simple loan. P dollars in the present, F dollars in the future. Now, there's another reason why this P dollars has the letter P. It's because the amount of any loan that's, in this case, I receive, has a name, and that name, of course, is, as some of you may know, the principal. Okay? So the principal is the upfront amount that the borrower got, and what the lender gets back in the end is F. And of course, that means that we can define some notion of how profitable was this loan to you, the lender. What you ultimately end up getting is this difference, right? F minus P. That is the profit that you got from lending out P dollars to me rather than, well, whatever else you could have done with P dollars now. And of course, this difference also has a name, and that name is interest. So the interest on a loan is this difference between the amount of the principal and how much the lender gets paid back at the end. Now, the interest is not a very useful concept because very often what we'll want to know is not how much did the lender get, but rather how much did the lender get per dollar that they lent, right? Or how much did the borrower have to pay per dollar that they borrowed. So that's useful because it gives us a notion of, from the perspective of the borrower, let's say, the cost of borrowing $1. For the lender, it's the profit, let's say, from lending $1. To get that, of course, we want to divide this total interest, F minus P, by the number of dollars that were lent, which was P. And when we do that, we're no longer defining this as interest. This is now an interest rate because it's per dollar that was lent. So that's our first definition. It's intuitive. You may have known it already. Excuse me. So interest rates are very often written in terms of percents. So I'm going to just remind you, this is true for any fraction. you can express it in percentage terms by simply multiplying it by 100. Okay? But you do need to remember, of course, that when you write it down, if you ever come across a problem where you need to compute an interest rate, you gotta make sure that it's clear whether what you're writing down is intended to be a fraction, which is fine, or whether it's a percent. That's fine as well. Just need to, if the percent is there, then I know you mean percent. If the percent isn't there, then presumably you mean it's a fraction. So like, for example, 10% is the same thing as 0.1. Take 0.1, multiply by 100, and you get 10%. Okay? So that's the first thing. Now we're actually going to take this definition of the interest rate and do a lot with it. So let me write it again over here. Let's say I equals, so little I is going to be the interest rates, is f minus p divided by p. Now if we arrange this equation, we can actually do all sorts of things with it. Notice that if you knew any two of these things, you could figure out what the other one is. By definition, if you know what f and p are, you can figure out what the interest rate I is. But also, we'll see that if you knew what I is and what p is, then you could figure out what f is. So if you're borrowing $100,000 at 10% interest rate, you could use this to figure out also, well, how much do I have to end up paying in the future? You just have to rearrange it. And similar, in principle, if you knew what f is and what I is, you could back out what's p. Now, it's not obvious why you'd want to do that in this context, but that's what we're about to discuss. So let's multiply p. Let's multiply both sides of this equation by p. We're going to get pi equals f minus p. Okay, that's where we started, right? pi is the total interest. But it's still the same equation, right? We just rearranged it. Now let's do something else. Let's add p to both sides. Then you get p plus pi equals f minus p plus p. Of course, minus p plus p is 0. So that just disappears, and we're left with this. Notice p is just 1 times p. So we can factor p out of this side and get p times 1 plus I equals f. Now this equation is going to be useful. It's just the same equation, really. But we'll leave it there because we're going to make use of it in a sec. Finally, divide both sides by 1 plus I. Here you get p over 1 plus I over 1 plus I, which of course is p times 1. So that cancels. Equals f divided by 1 plus I. Now this formula is an example of something broader that we're going to look at today, which is called the present value formula. And again, it's just a reorganization of the definition of the interest rate that we had there, but actually has a lot of content. And what it does is it tells us the following. Suppose you, well, the interpretation of a loan, what it's saying is, suppose that there is some payment F that you need to make in the future, and the interest rate is I. This tells you, well, what the principal must have been in order to, behind that contract. But more generally, what this can be used is to kind of convert future payments into a present value, into something in terms of dollars today. So for example, suppose I know that in 1 year I'm going to need to spend F dollars. Let's say maybe, suppose my kid is going to go off to college next year and F dollars is the tuition for next year at GW. Then, and I know that if I put money in the bank, it's going to earn interest of I per I, right? I is the interest rate. What this formula tells me is that how many dollars I need to set aside now to make sure that after 1 year has passed with that interest I have F dollars. So let's now use this to generalize. This was for payment 1 year from now. But as I mentioned earlier, we're going to want to be able to do this for payments of multiple different dates. So let's look at another example. Suppose actually you're going to lend me P dollars now in exchange for F dollars in 2 years. Of course, I could run the same formula and say, okay, then there's a 2-year interest rate that I can compute with the same formula. But that isn't going to be very helpful. Ideally, if I suppose you give me the choice, you can do this loan contract with me for 1 year, or this other contract with slightly different numbers perhaps, but it's for 2 years. How would I be able to compare which one is or isn't a good idea? Well, to see that, let's do the following. Remember that if you lend me P, that's actually from here. If you lend me P dollars and we wait 1 year, then the amount that I have to pay you back is P times 1 plus I, right? I have to pay you back each dollar, that's the 1, and for each dollar I also have to pay the interest, that's the I. And notice I put the 1 there to indicate that this is for a 1-year loan. Now, what if at the end of the year you decided, and I agreed, that you're going to lend all of this back to me for another year at the same interest? Then we would have some F2, which is what if we'd instead waited an additional year before I paid you back? At the same annual interest, you take this F1, and again, it's being multiplied by 1 plus I, because at the end I have to pay you back each dollar, and for each dollar I also have to pay back the interest. And then notice that I can replace F1 here with the F1 from there, which equals P times 1 plus I. And so what I end up with is that F2 is equal to P1 plus I times 1 plus I, or P equals 1 plus I squared. Divide both sides by 1 plus I squared, and what do we get? We get P equals F over 1 plus I squared. And if you're thinking, oh, so in order to get an annual to use this to get an annual interest rate behind any loan contract like this, all I need to know is how many years it's going to last. And then I can just figure out the relationships here by saying that F equals 1 over 1 plus I to the power of however many years it is that the contract lasts. And you would be exactly right. So let M equals the number of years the loan lasts. And there's a reason why I picked M. It's because M has a name, and that name is maturity. Then we will have this general formula for the present value of F dollars that are going to be paid to you M years from now. Okay, so this formula is going to be our ticket to try and make sense of possibly much more complicated contracts than the one that we're looking at here. Here we have just one payment now and then one payment in the future. We'll see that there are other kinds of loans where there may be lots of different payments. And this present value formula is going to be our way of trying to make sense of them. Any questions, comments? If not, then let's move ahead. So before going further, let's start by writing the present value formula up here in the corner. So we have it at our disposition. And let's move on to the next kind of loan. First, we looked at the simple loan, one payment of principal, and then one repayment at a future date. Let's instead, sorry about the racket back there, think about another kind of loan that came up actually in class earlier. Remember, at some point I was discussing mortgages and mortgage-backed securities. The mortgage, of course, is just a loan to buy a house. And let's say that I borrowed some amount to live in the house that I'm in right now. With mortgages, typically, you don't pay back one lump sum. So when I buy this house, let's just pretend I borrowed $1 million. It's a 30-year mortgage. It's not the case that I have to now wait 30 years and then pay back, let's say, $2 million. That's not how it works with mortgages. Mortgages generally, instead, you have payments every month over 30 years, and that payment is some constant number. So what we're looking at are fixed payment loans. When you borrow to buy a car, usually it's also a fixed payment loan. And it's the first part of this contract is similar. You lend me, or you give me P dollars now. What's different is I pay you some other amount, let's call it C dollars, each year for M years. And that's it. That's just how the contract works. So instead of one big lump sum after M years, I'm paying you piece by piece by piece. How do we figure out the interest? Well, for sake of example, let's suppose M equals 3. So you're lending me P dollars and I'm paying you back C dollars next year, again C dollars in 2 years, and again C dollars in 3 years. What can we do to try and figure out what is the interest involved here? Well, let's try a simpler question. One thing I can do is use the present value formula here to think about the present value of each of these 3 payments separately, right? So why don't we do that? So the first payment is C 1 year from now. And we want to know what's its present value. The present value of C 1 year from now, of course, is, if we knew the interest rates, C over 1 plus I. That's straightforward. What about the second payment? That's C dollars 2 years from now. Its present value is not C. If you knew what the interest rate was, it would be C over 1 plus I squared. And then there's the third payment. It's C in 3 years. Of course, that'll be worth C over 1 plus I cubed. Notice that since all of these are now present values, they're all in terms of their value, their worth today, and that means that I can actually add these things up to get the present value of all three of them. And if I do that, I'm going to get some number. Of course, I am getting from you P dollars in the present, right? So the interest rate that's implied on a contract, on a fixed payment loan like this one, is going to be the interest rate that satisfies this. It's the interest rate that makes the present value of the three payments equal to the principal. Of course, this is a complicated equation. It's going to be arranged to be a cubic polynomial, and so I wouldn't expect you to be able to solve this in your head or on paper unless I'd set it up so that it had very simple numbers. But if you were to be given these numbers in principle, you could do it with a calculator or Excel. And the most important thing to keep in mind is that there is one and only one interest rate that's pinned down by this procedure. So just to see that, suppose this is I, and suppose this is present value of the sum, and suppose this is P. Suppose you set I off to infinity. If I goes to infinity, what's going to happen? This sum is going to be going smaller and smaller and smaller and go to zero, right? So we know that for very large interest rates, the present value of the sum is very small. As we make I lower, of course, you should see that you're making the denominator smaller, which means that each of these separately is getting bigger. That means the sum is getting bigger. And that means this present value of the sum is strictly increasing, right? As you raise the interest rate, as you lower the interest rate, you're raising the sum of the present value. And as I goes to zero, what do you end up with? You end up with 3C. So as long as 3C is higher than P, there will be one and only one positive interest rate that makes sure this sum equals exactly P. So again, it might not be something that you could compute in your head, and in general, we won't be looking at fixed payment loans in this class anyway, because they're not very tractable. But in principle, you could use a calculator or some other tool to figure out the unique interest rate that solves that equation, okay? So that's our first example of using the present value formula for trying to deal with multiple payments at different dates. You just apply it separately to each one. I'm going to say there's a very common mistake that people make in this class, which is they think, oh, there are three payments of C, and so I just take the three C's and then discount it 3 times. That's wrong, right? It's wrong because each C is at different dates, and therefore it has to be discounted separately. Let me give you another example. Remember, we were using an example of my son, who you may have seen was running around behind me a minute ago. He's not going to GW next year, but let's imagine, for argument's sake, that he's going to start college next year. And the thing about that example that didn't quite fit before is that it's not true that I have to plan to pay tuition for 1 year, right? GW takes 4 years. So GW costs, let's just say for sake of argument, $60,000 for 4 years. And my problem is, how much do I need to save in order to make sure that I have enough? Let's say I can earn interest rates I, whatever I is, 10%, 1%, whatever the bank tells me. The question is, how much do I need now if I want to make sure that I have a college fund set aside that's going to pay for the 4 years of tuition? How would I do it? Well, here are the 4 payments of 60,000. I'm just going to write 60K, 60K, and 60K. How much money do I need to have set aside to make sure that I can afford the first year of tuition? We did that exercise already. It's 60,000 over 1 plus I. Separately, how much money do I need to have set aside in order to make sure that I can cover the second payment? It's in 2 years, so the present value formula says the answer is 60K over 1 plus I squared. Applying the present value formula, the third payment would be this, and the fourth payment's present value, the amount I need to set aside to make sure I can pay that in 4 years, is this. So how much do I need to set aside in total to make sure that I have enough in my college fund to pay for 4 years of GW starting next year? It is the sum. And so that would be the answer. I just need to know the interest rates. I could plug it in and solve it to get the answer. Let's say if my bank pays 1% interest on deposits, then 1 plus I would be 1.01. There. Okay. So that is a fixed payment loan, and we used it to think also about paying for college, which is a slightly different, which is not a loan, but again, the idea here is to try and value streams of money or payment streams where the payments may occur at different dates. You can figure out the present value of the whole thing by applying the present value formula separately to each one and then adding them all up. And you can add them all up because now they're all in the same terms. They're all in terms of dollars today. Any questions, comments, thoughts, doubts about this before we move on? All right. In that case, let's move on. Next, I want to talk to you about a different kind of financial asset, which you may have heard about, and which is going to take up a lot of time during the semester. And that is a kind of asset called a bond. Bonds are the way in which companies often borrow, and they're the way in which governments usually borrow, and that's why it's going to be very important for us to know what they are. And the way a bond works is that it's a contract, and the contract says, I will pay, I am the borrower. I'm going to leave it blank. Before, this contract said, I will pay you, right? Lender. Actually, let me write it here. F dollars in M years. That's similar, right? Except that instead of saying I pay you, whoever the lender is, it says I pay whoever owns this contract. It would probably say something like the bearer, right? That's what it says on money. I will pay the bearer, I will pay whoever owns this contract F dollars in M years. Where's the principal? The principal is not written into this contract. In fact, it's nowhere to be seen. So how can I borrow money with this contract, this piece of paper that says, I will pay F dollars to whoever owns this? The answer is that I will sell it. So I can sell this bond to you or to anyone who wishes to buy it. And then how much money have I borrowed? The amount of money that I've borrowed is however much you paid me for the contract. So this P dollars, the principal, is the same thing as the price we agreed for the bond. Interesting. So the contract itself doesn't specify P. P is just determined by, well, what I can persuade people to give, to how much I can persuade people it's worth paying for this contract. And as soon as that happens, as soon as we agree on a price, we've now also agreed what the interest rate is, right? To get the interest rate, I just need P and F. P isn't written in the contract, but as soon as you agree to pay me some money, then we determine that interest rate. So for example, suppose, just to use some easy numbers, suppose F is 110. And let's say M is 1. And suppose people agree to buy this for $100, then, well, present value formula, P equals F over 1 plus I. P is 100, F is 110. We don't know what I is, but this is one equation with one unknown, so the answer shouldn't be far away. Multiply both sides by 1 plus I, and divide both sides by 100, and we get 1 plus I equals 110 over 100, which is 1.1. So that tells us I is, you can say it's 0.1, or you can say it's 10%. Okay? So that's an example. And as you can see, the structure of this thing is exactly the same as a loan. It's P dollars up front with F dollars in the future. As soon as we agree on a price, as in this example, we've implicitly agreed on what the interest rate is. And so sometimes when you read about what's happening to bond markets in the news, sometimes they talk about what's happening to bond prices. Sometimes they talk about what's happening to interest rates. Now, there are no interest rates written down, excuse me, but if you know the bond price using this formula, you know what the interest rate is. One thing you should notice is that notice that I is in the denominator. So if I is going up, it's the same thing as saying that P is going down, and vice versa. And it's just by definition. The bonds that we're looking at are bonds that have no payments other than F in the future at, after M years. But in practice, a lot of bonds aren't actually like that. In practice, a lot of bonds are slightly more complicated. What they do is they have the following structure. I pay, again, the bearer, whoever owns this thing, F dollars in M years, but they'll also say, and C dollars each year until then. This C dollars is called a coupon payment. And these bonds are called coupon bonds. The bonds that we started with, which don't have a coupon, are also known, therefore, as zero bonds, because the coupon is zero, or they're maybe sometimes known as discount bonds, and the reason is because you're buying a promise of F dollars. In general, you're going to pay less, right? Because otherwise there would be no interest. So it's as though you're buying F dollars at a discount. That's why they're called that. Okay. So again, this coupon bond kind of looks like a mix of a simple loan and a fixed payment loan, or maybe it's just like a fixed payment loan, except that the last payment is bigger. And if we wanted to value it, we would use the same present value formula as we did before. Right? We would just need to value each payment C and F separately. Now, the idea of getting these C dollars in between as you wait is kind of like the idea of having borrowed F and then paying in a little bit of interest each year up until then. And you could define, just as we defined the interest rate before as being, well, in the way that we did using the present value formula. Similarly, you can define C over P as a coupon rate, okay? But it's very important that while you're getting these things that look like interest payments, these coupon payments, throughout the life of the bond, it's not true that the two, interest rate and coupon rate, necessarily bear any relation to each other, right? There's no reason why you would apply the present value formula to these coupon payments and the face value. This F is known as face value, by the way, which also conveniently starts with F. There's no reason why when you set up the present value formula for this, all the payments you get from a coupon bond, and work out the interest rate, there's no reason why it should bear any relation at all to the coupon rate. They're just independent things. It depends entirely on what price you happen to agree on. So just keep that in mind. So again, the bonds look like loans in terms of their payment structure, but there is one thing that makes them distinct. And that is due to the fact that, remember, this loan or this bond doesn't say, I will pay you, whatever your name is, who lent me money. It says, I'll pay whoever owns this contract. And that's a big advantage to you, the lender, because it means that, okay, let's say you lent me F dollars for 1 year, and we agreed the price 100. Sorry, we agreed the price 100 for a loan. That means I have to pay you 110, right? And if you held on to it for a year, it would be like you getting 10% interest. Right? That's the same as with a loan. But what if 2 days later, you suddenly change your mind and you think, oh no, I need the money now. I can't wait for a year because of whatever reason. With a loan, too bad, you're stuck. You have to wait for a year before I pay you back. That's the contract, right? But this bond doesn't specify who the lender is. So what you could do is you could take this bond and find someone else to send it to. Sorry, find someone else to sell it to before the year has passed. In other words, there's a secondary market for these things, whereas for loan, typically there won't be. And that's a great convenience to you, the lender, right? You know that if you need to get rid of it quickly, as long as it's a liquid asset that's widely traded, you'll be able to get the money sooner. The price you get may not be the same price you paid, right? It may or may not be equal. But the fact is you're still able, you don't have to, you're not forced to wait for an entire year. This asset is more liquid than a simple loan because there's a secondary market for it. Any questions, comments about that? All right. There is one more kind of asset that I want to look at today, which is one where it's a bit like the coupon bond, actually, except that there is no maturity. How can that be? Well, that kind of asset is called a console or perpetuity. And it says something like, I will pay, again, the bearer, whoever that is, whoever bought this thing, whoever currently owns this contract, $C each year forever. Have these things existed? Yes, they have. I believe the British government sold this kind of bonds to try and raise money to fight Napoleon. In any case, you would say, why would you buy an asset that's going to pay forever? Well, again, you can sell it before it's expired, so you don't actually literally have to wait forever. You can sell it to someone else. What the British government was really doing is they were trying to borrow now, and then at some point in the future, they would themselves buy back these bonds, since they weren't sure when they were going to be able to pay back. They figured, we'll borrow forever, we'll pay $C each year forever, but eventually, whenever we can actually afford it, we'll buy back those bonds, and then of course we don't owe anybody anything. So still, the question is, how would you figure out what's the implicit interest rate here? And the way you would do it is like this. Let's just say P is the principal, or the price rather, and let's just apply the present value formula separately to each payment. So the first payment of C is discounted once. The second one is this process of bringing things back to the present is sometimes called discounting. The second one, we apply the present value formula for 2 periods, so it's 1 plus I squared, 1 plus I cubed, and so on to infinity. Okay, how do we compute that? How do we figure out if someone agreed a price P for some console C, what is the interest rate that they ultimately agreed to? There's a trick for dealing with infinite sums, and I want to show you because it's very useful. Even if, well, some of you may know it, some of you may not. I'm going to write below here is P divided by 1 plus I. What's that? Well, I take each of these terms and divide by 1 plus I. So the first term becomes C over 1 plus I times 1 plus I. Of course, 1 plus I times 1 plus I is 1 plus I squared. Take the second payment, divide it by 1 plus I. It's 1 plus I squared times 1 plus I, which is 1 plus I cubed, and so on. Right? It's going to look just like the first expression, except that each one has a power that's larger by 1. And now here is the trick here. Subtract the bottom series from the top series. So p minus p over 1 plus I. What do we get? Well, we add c over 1 plus I plus c over 1 plus I squared. Don't forget the parentheses. Plus c over 1 plus I cubed, and so on. Minus all this stuff, right? Minus c over 1 plus I squared minus c over 1 plus I cubed, and so on. And what you should notice is that this number here, the second term, is subtracted. So it's going to cancel out. This number here is also subtracted, so it's going to cancel out. And indeed, that's going to happen to every single term in this series. Each number up here is going to be canceled out by a number down here, with one exception, the first one. So the first term isn't going to get eliminated in this way. And so p minus p over 1 plus I is c over 1 plus I. Now, multiply both sides by 1 plus I, and we're going to get, okay, p times 1 plus I is just that. P over 1 plus I times 1 plus I is just p. And c over 1 plus I times 1 plus I is just c. Expand over here, and we get p plus ip minus p equals c. P minus p is 0, so we're left with just ip equals c, or p equals c over I. So when you have an infinite payment, a payment of c each year forever, starting next year, the formula for that turns out to be very straightforward, and it's just this: p equals c over I. So that's how you would be able to still use a present value formula here to figure out what's the interest rate that's been agreed when you observe someone buying perpetuity. Any questions, comments? All right. Let's see, we have 25 minutes left. That's good. What this discussion has raised now for at least the second time is that very often when you buy an asset, when you buy a bond in particular, because there's a secondary market, you may not be planning to hold it until maturity. Maybe planning to sell it earlier, and certainly you can sell it earlier. In the case of the console, that's obvious because you can't wait around forever, literally, for all the payments to materialize. So what we've discussed so far, this interest rate that we have, has a name, and it is yield to maturity. And it tells us again how much you're getting paid per dollar that you lent in an annual basis if you hold the bond until maturity. But if you sell it before, we would need a different concept to figure out how to think about your profit rate. So let's take an example. Let's say there's a coupon bond that lasts M years. So M is the maturity, but you sell it after 1 year. Okay. Now we'll need a little notation for this. Let's say that the price at which you bought it this year, right now, is price P with a little t. So little t denotes the date at which you bought this thing. And you sell it at a different price. Well, it may or may not be different, but there's no reason why it should be the same, because after a year, you may have new information about how valuable this is. In addition, a year has passed, so it's closer to maturity. Let's say you sell it at price P t plus 1. So like if t is the year, then P of 2021, and then you sell it at next year at P 2022. Okay. What profits will you have earned on this bond over that year? Well, one source of profit is that you received a coupon payment, if there is one, right? It might be zero if it's a discount bond, but it'll be positive more generally. And the other thing that you should have received is that you're buying this thing at date t and then selling it again at date t plus 1. So another source of profit for you from buying a bond today and selling it tomorrow is that the price might have changed. In particular, you're going to benefit if the price has gone up. So this, of course, is just the coupon payments. But this price difference between you buying and selling an asset also has a name. And it's called, this is important, the capital gain. Okay? So keep that in mind. And just as when we were talking about this for the case of interest, interest is useful to know, but much more useful is knowing how much interest you get per dollar that you lent in the first place, right? So we took F minus P, which is the interest, and divided it by the principal P to figure out how much interest are you getting per dollar. And we're going to want to do the same thing here. As is, we just have the total, right now, we just have the total amount that you profited, right? You have C, and you have any price change. You add them together, you get what's called the return on the asset. But again, we may want to have this scaled by how much are you getting per dollar that you lent in the first place. If you got that, you would get what's called the rate of return. And just as before, what we want to do is you want to scale both of these divided by how much you lent, the principal. And with a bond, of course, that is just the bond price itself. So this is the rate of return. It's very important to keep it in mind because it's going to matter anytime you are holding an asset and not until maturity. So today we looked at two different formulae, and so we very quickly ramped up how much math there was in the class. The first one was the present value formula, which you should always remember, which is useful for trying to compare sums of money that are being paid at different dates. You just compute their present value and add them all up. And the second one is this one. This is the rate of return, which tells us how profitable it is to buy some assets and then sell them before their maturity. Okay. Now, next class, what we'll do is we'll go over some examples of rates of return. And we've run out of time today, but we'll be able to see a little bit better what we can learn from rates of return about the pros and cons of holding different kinds of bonds. Okay. Any questions, comments? Capital gains. Sorry. Before we move on. Once we divide it by price, this is no longer the coupon payment, but it does have a name. This is the coupon rate. And once we take the capital gain and divide it by the price, again, it's a rate because it's per dollar. So this is a capital gains rate. That's important. Capital gains are something that pop up in politics every now and then if you read current affairs, because in this country they've been arguing for decades about the right amount, about how much you should tax capital gains. So if you heard about capital gains taxes and didn't know or weren't sure what capital gains were, this is all it is. It's the gain, the increase in the value of an asset that you're holding, although you might sell before maturity. Okay, so if there are no questions or comments, then I think it's time for our exit check meeting. Here we go. Get ready. First question. Bonds are like loans, except that unlike loans, bonds have a secondary market, bonds have a primary market, bonds are debt, or bonds are equity. One more person. Very good. Most of you got that right. Bonds and loans are both forms of debt. Question 2. A rise in the price of a bond implies a rise in the bond's interest rates, a decline in the bond's interest rates, a lower coupon payment, or a lower capital gain. Very good. That was a trickier one, it seems. All right. If you lend me $100 at a 10% annual interest rate for 1 year, next year I pay you how much? 100, 110, 120, or 121? Waiting for one more person. 7, 6, 5, 4, 3. Okay, excellent. Everyone got that right? Congrats. Marshall is on fire, it seems. All right, if you lend me $100 at 100% annual interest for 2 years, in 2 years I would pay you how much? Remember, this is a 2-year loan at 10% interest. Ten seconds to go. Aha, yes, that was a tricky one. Let's see next. Almost there. With coupon bonds, the interest rate is always equal to the coupon rate, is always above, is always below, or maybe above or below the coupon rate. Which one of these is right? Everyone's having to think hard about this one. 3, 2, 1. Yeah, this is a harder one. It could be either way. And last, the percent increase in the value of an asset is the what? Capital gains rates, rate of return, yields maturity, or interest rates. The percentage increase in the value of an asset. Ten seconds. Going once, going twice. All right, let's see how we did. Third is Alexandra C. Congrats. Second is Richards. And number 1 is Marshall. All right. Good job, Marshall. So, Marshall, you get to put something silly on my face. Your phone froze, Marshall, but are you able to hear me?
Yeah, I was not able to answer last question.
Well, you won
Anyway,
anyway, unless there are two Marshalls in the class. So,
I guess I'll do cat this time since I have two cats.
cats. Okay. How about pat on head?
That's great. That's great. That's a good
I
one.
really, yeah, I don't know how they do it.
Amazing.
But anyway, congrats. Good
Thank
job.
you.
Yeah, I don't know how they do this kind of stuff. So, all right. Thanks for coming. Take care. Enjoy your cats, whether they're on your head or in your house. And well, we'll talk next time then. Thanks very much.
Have a good day.